Oh, okay, I think we are ready to begin the after lunch session of the day, and Sayan Choudhury will continue his lectures on driven quantum many-body system.
Hold on. Okay, I'm connected, right? Okay, great. Thank you. Okay, so I know this is the tough session because you're after lunch, and there's a lot of motivation to sleep off. So, um, so please ask questions so that all of us stay awake. Okay. Okay. One thing that I missed last time was I didn't give you any references for anything that I was doing. So I must start off by giving references. So the two main references for these parts are, there's this review from the group of Polkovnikov, it's Marin Bukov and others. Strictly not Polkovnikov at all, it's Bukov et al. This is an old review now. It's 10 years old. It's more than 10 years old. It's very pedagogical. It will introduce you to many details of how we actually look at flow case systems. And it will help you sort of go through a lot of the algebra. And because it was done at an initial time, I think it's very detailed. So it's a nice place. The other one is this, which is from Mark Rudner and Nathaniel Lindner, which is, I'll give you the archive reference. There's also a Nature Reviews Physics paper on this. This one is called the Floquet Engineer's Handbook. Again, this has many, many details. Because this one comes later, it's got sort of more better set of citations and so on. But yeah, these two are the primary things that I have been following for these couple of lectures. Then as we go ahead, there will be more specific things from specific papers. So those I'll mention as we get along. Okay, but let's then start off where we had left. Okay, so let's start off. So the question that we were doing was that of putting electrons in a tilted field, right? So you turned on a field, and what we were looking at is that if you do turn on the field, then you can get localization. This is the famous Stark localization. But what we did in this process was we started off with a Hamiltonian that was actually time independent, and we made a rotating frame transformation to make it time dependent. Okay? And one question that came up at the end was, what if we actually drive this field in some way, right? So let's do that. Actually, this is a very interesting problem as it turns out. So let me write down the Hamiltonian. So this is simply a tunneling, and now I add this term where now instead of having a delta, you have a omega cosine omega t sum over j and j. Okay. So this was first looked at by Dunlap and Kenkre in this 1986 PRB. Okay. So now you know what the first step is going to be. You want to take a transformation that will kill off this term, right? So you will have some p of t such that this imaginary part there will kill this off, right? So that is the motivation. So then what's the p of t? The p of t that we take is e to the power minus ia sine omega t j and j. Okay. So you can see why this will work, because when I do the p dot, what will come out of this is a omega cosine omega t, right? And that will take care of this term. Okay. So what we get then after the transformation in the rotated frame is the following. Okay. So this is fine. This is exactly what we had done last time with you have a sine omega t coming here instead of delta t. Right? Okay. Sorry. So actually it is the fictitious force that has cancelled off the time dependent part. So whenever you are able to get such a nice construction, yes. Okay. So turns out that that part itself is not that difficult to do, because that you can engineer. You are still left with this problem that you have not really gotten rid of the time dependence, right? So you have just taken it from one place and transferred it to another place. So it's just that sometimes in this process you might be able to do a transferring where after which calculating the Floquet Hamiltonian might be easier. So this is what I will show right now, in fact, with this. Yeah. Yes, please.
So same like transform Hamiltonian you would have gotten from the interaction picture.
Yes, absolutely.
So, what's the motivation from Floquet?
So essentially, see, again, the interaction picture works typically when I have two well-defined. So the way we have usually set up the interaction picture is we have a h naught plus v of t, okay, which is true here. But you may have a situation where you are actually both your parts are time dependent. You have a h naught of t and a v of t. You find a way to kill off the v of t and transfer things into h naught of t. Okay, so this is a more general construction. Okay, so all that I want to say is that the interaction picture is a more specific case of doing something similar. Okay, so you end up with this Hamiltonian. So one has to now find from here how do we get the Floquet Hamiltonian. Okay, remember this is not the Floquet Hamiltonian, because after all the Floquet Hamiltonian would be that if I was able to do a rotating frame transformation that made this time independent, that would be the Floquet Hamiltonian. This is not the Floquet Hamiltonian. This is just a rotating frame Hamiltonian. But I can find the Floquet Hamiltonian now in this rotating frame if we go to the high frequency limit. Okay, so if we are in the high frequency limit, HF is approximately the averaged Hamiltonian. Just keep it like this. Okay. Now I'm going to use a formula that hopefully at some point in your life you have encountered, which is an integral expression for the Bessel function. So this kind of thing, this e to the power minus ia sine omega t, if I take this integral, I'll end up with Bessel functions of the first kind, right? And if you plot the Bessel functions of the first kind, you'll remember that this goes like this, right? So what this means is that once I have done this, once I have taken this average, what I get is this J here, this HF becomes minus J effective AJ plus 1 dagger AJ plus the Hermitian conjugate where J effective is J by J times J naught A. This is clear? Okay. Now let's look at what happens when we have one of these zeros, right? So let me call this, let's say, A star. So I think this formula I think is not with omega. This just gives you J naught A because omega sort of comes in here, right? Yeah. So when you now go to any of the zeros of A, your J has become 0, right? So then what you get is by tuning this A, the rate at which you are driving this, right? You can localize the particle, okay? Because you can get to an effective Hamiltonian which is 0, right? So this tells me that these zeros of A, this corresponds to dynamical localization. Okay. Good, clear?
So I have a question.
Yes, go ahead.
So when you are driving very fast,
Huh.
then
Huh.
the average Hamiltonian is the fluid Hamiltonian, right?
Approximately. There are corrections, but approximately is true.
But you are taking the average in the rotating frame. What if I take the average in the lap frame?
Yes, so you can take the average in the lap frame. You see, the problem here is with your lap frame Hamiltonian has A omega cosine omega t. So your lap frame Hamiltonian is such that this term scales with omega. Okay, so doing a naive lap frame thing won't work here, okay, because of the scaling. So in fact, when we will do these additional sort of how one gets H effective or HF generally, whenever you have this kind of scaling, then you would find that there are additional terms because we can't just do the average, because there are other higher order terms which will also contribute. On the other hand, once I've gone to the rotating frame, then I can do this average, there is no problem, because now I no longer have any term here that scales with omega, right? So that's the reason why I am doing this in this rotating frame.
Probably this is saying like that each if terms you can write it from local conditions. This is the first term.
So that is exactly, so we will, as we go along today, we will do Floquet Magnus, and one of the things that you will get is that if I did naive lab frame for Floquet Magnus, we cannot ignore higher order terms because there will be terms that will scale with omega. So that's why you need to keep those terms. Okay. On that note, before we, so I will sort of be building on this statement that he has made of how we calculate effective Floquet Hamiltonians, but yeah.
So if there is no high frequency limit, if omega is not large, then what we can do?
Then there is no, so typically there is no good way to do a perturbative expansion when omega is not large, typically. But what you can do is, if you have, even in the small omega regime, if you are driving with a, if your driving field's amplitude is very large, then you can do what is called a Floquet perturbation theory. Okay, so you can do this in two, and there you can do it exactly by going to the interaction picture. So essentially you need something large to be able to do an controlled expansion. Okay, so high frequency always gives you a way to do a controlled expansion. Otherwise, you would need certain some other scale to be very large. Okay.
Taking A large, I don't think this type of analysis will work.
No, so taking A large over here wouldn't work. Okay, but I mean, one of the things you can imagine is the following. Here, the problem that we have in doing the naive Floquet thing is, I have A omega cosine omega t, and the naive lab frame Hamiltonian, what it is doing is that there, that term is increasing, as I take this high frequency limit, and so what we are doing is we are transforming into a rotating frame. So typically when you have such a something which is large, okay, what you can do is, in a manner analogous to this, you can actually shift to a rotating frame, and when you cancel off that term, in the rotating frame you would have a time dependent problem where you can now perform Magnus, okay, or now perform any of these high frequency expansions. Okay. The other thing which we will come in at the very end is that, as you will see, that high frequency is also the region which is good for Floquet engineering. So it is also useful to develop high frequency expansions. But building on this, let me just mention one final thing before we go to actually build some of the machinery of calculating this, which is the following. So this is based off one of the sort of what I think was an important example of Floquet engineering in its early days, and this is based on the driven Bose-Hubbard model. So the theory is from Andre Eckart. I think this is a PRL from 2007, I want to say. And then there are lots of experiments from the group at Hamburg. So let me just very briefly tell you what the Bose-Hubbard model is. So the Bose-Hubbard model features bosons which are hopping on a lattice. You have an interaction term, okay, and typically we also put in a chemical potential. So this is much simpler than working with the Fermi-Hubbard because these are bosons. The phase diagram here looks like this. This is mu by u, this is j by u. You get these lobes, So I just wanted to mention this. So what happens is that typically this model is famous because it features a quantum phase transition between a superfluid and a Mott insulator. Okay, and what was done in this model, in these kind of experiments, were that they actually tried to do modulation just like this. So the modulation that they did, in particular in these experiments, these ends. Oh, good. So this is in the Mott insulating phase, you have an integer number of particles sitting on each side, lattice side. So here you have one particle on each side, this one has two particles on each side, and this you tune by tuning mu, the chemical potential. Okay. Interaction is on site because these are bosons, so you can have bosons sitting on each side, right? So you can see that if I have one particle, this is 0. If I have two particles, this becomes 1. If I have three particles, then you'll see this becomes 3 and so on. Yes, that is generally nearest neighbor for this particular model, but you can even take this to be longer range and so on. Okay, so this has been a model that has been of sort of interest in, at least within the cold atom community, because this was the first experimental observation of a quantum phase transition with cold atoms. So they put in bosons in a 3-dimensional optical lattice, and they were able to see this phase transition. So this was a very sort of seminal work in 2001. So here, one thing that was done in these experiments from Klaus Schengstock's group at Hamburg, what they did was, yes, please. Oh, this is because I've taken this to be nearest neighbor. Okay. So this does include the, yeah. So if I was writing it in 1D, I would have just written as sum over I and then explicitly kept I plus 1 and the Hermitian conjugate. But because this is for general, and actually 1D here is special for its own reasons. It's the lobes are slightly different. Okay. So this was the model that was created, where you were driving this no longer with a term that scales with omega, but you have just some k cosine omega t. Okay. So now what happens with this is your after flow k, you actually get a HF with minus J effective Ij, Ai dagger Aj, plus all the other terms, okay? And this J effective now, this J effective is now scaled, just like what we had done there. So this J effective now gets scaled with J naught. By omega. So one thing is that even when I have the interaction term, my rotating frame transformation is such that it commutes with the interaction term. Okay, because the interaction term is just on site, so there is no additional term that goes. So the rest of the terms do not change at all. You only have a rescaling of the hopping. Okay, so this means that by changing my driving amplitude, I would be able to create a superfluid to a Mott insulated transition. Okay, and also you can do things which are more complicated. You can change driving amplitudes in different directions. Okay, and they had used this to make the driving amplitudes, keep it positive in one direction, make it negative in another direction, and so on. And because you see that the Bessel function also goes down to negative values. So you can make it positive in one direction, make it negative in another direction. So by playing around with this, so the essential sort of take-home message take-home that I want to give you with all of this is high frequency driving can be used to generate or engineer rather desired effective Hamiltonians. Okay. And this whole thing is the sort of sub area of Floquet engineering. You come up with interesting ways to drive the system, and through which you would find different kinds of effective Hamiltonians. Okay. So I told you, so everything that I told you, of course, is that high frequency is good, but everything that we have been doing so far really has been to focus on the averaged Hamiltonian. And one question then is that if I want to go beyond the average Hamiltonian, I must have a way to do an inverse frequency expansion, right? Where the average Hamiltonian is really like taking it to this limit of being extremely fast driving, right?
Just one question.
Sure.
After we add this property, what is the interesting thing happens to this model?
So the thing is that once I add this, right, I can see if you tune your J, you can go from the superfluid to Mott insulator, right? Usually the way people had done it earlier was they would put these atoms in some optical lattice and then they would increase the depth of the lattice. The point here is that you can do this by driving the lattice. Okay, so by driving the lattice, you can go from a superfluid to Mott. Okay, that is one thing. The other thing why this was also useful is what they did was they in the this is maybe a slightly side remark, but even if you are in the superfluid phase, I can make this J's value positive or negative depending on what my driving amplitude is, right? So what they were able to do was in 2D systems, sometimes, and particularly in the case of triangular lattices, what they did was they did this thing where in a particular direction J was kept positive, in another direction by taking it to a value where the Bessel function goes negative, J was made negative, and you are still in the superfluid phase. So in the superfluid phase, you can substitute these A's through their expectation values because superfluids are coherent states. And when you do that, you come up with classical spin models which are frustrated. So this became a way to simulate quantum simulate classical frustrated spin models. Okay, so this gives you, A gives you a way to control this quantum phase transition, B gives you a way for engineering Floquet Hamiltonians that you would not be able to get otherwise. For instance, this making J positive would be impossible to do in a standard setting. Okay. Another thing that was done, again, I don't want to get into these details, but you had this term of e to the power minus IA sine omega t. So I'm creating these J effectives, but these terms can come with certain phases. And then again, by engineering the Hamiltonian properly, you could engineer what are called Peierls phases, which correspond to certain gauge fields in the system. So you could create effective gauge fields and so on. So for these kind of Floquet experiments, this has been a very useful kind of strategy in cold atoms, that you periodically drive the system that will give you many, many things that the undriven system does not have. Yes, please.
So as you said that you change the driving by J, you change the, while having a phase transition, you change the J, right?
I'm changing the J, and how I'm doing it is actually by changing the K.
So initially you said in experiment they change the J to have the phase transition.
Yes.
But in your driving term, you are putting the potential term on the on-site.
So good.
Right?
So,
Similar, right?
so initially, so two things. One is that initially when this J was changed, you would change, if I am not putting this additional term, I would have to change J in some other way. Typically the way that this would happen is that what you do is you trap atoms in this sort of egg carton like boxes of light. Okay, so these are called optical lattices, and you increase the depth of these lattices. This leads to lower tunneling. Okay, this gives you an alternate method of approaching that. So the first interest was just simply that you have an alternate way of creating this phase transition, of controlling the phase transition. But then, as I told you, here you can also make the J negative. So you can actually do things that were not possible simply by changing the depth alone. So it gives you what we had and more.
So this omega is supposed to be high compared to what?
Omega is supposed to be high compared to all other local energy scales in the system. Okay, so so this will become clear. So this is a very good question actually. This will become clear once we do this inverse frequency expansions, which I will do right now. So then you will see this. Yes. Okay. Okay. So now we are going to work on developing a framework to calculate HF. Okay.
Can I ask something beyond?
Yes, please go ahead.
If you have some effect in element like HF,
Yes.
now you observe some evolution of an operator.
Yes.
So you get an effective picture with this effective Hamilton.
Sure, you do. Yes.
So what signature do you get when?
I mean, what do you want, for instance? Do you want, for instance, Krylov complexity? So you can, okay, so, but you want to ultimately take an expectation value of it, or what's the plan?
I am thinking that since this 2K energy eigenvalues, those are 2 pi periodic.
Yes.
So those are some star-like connection, because stars have all equispaced energy levels.
So these are not equispaced. Okay, it's just that everything, all the energies are 2 pi periodic. That has the consequence of that is actually very bad, as I will tell you tomorrow, I guess, or maybe day after. The consequence of that is actually very bad, because what it really corresponds to is that your energy in scattering processes here, your energy is only conserved modulo 2 pi by modulo h bar omega essentially. Okay, so you can have much more scattering compared to your standard scattering processes which only conserve energy. Okay, so one of the consequences of all of this is that if you generically drive an interacting quantum system, it will heat up to an infinite temperature state. Okay, yeah, I'm sorry I'm preempting this, but we will talk about this more. The good news is that when you are in this high frequency regime, where your frequency is much larger compared to local energy scales of the system, this effective Floquet Hamiltonian can describe the dynamics of your system very well up to exponentially long times. So not only is high frequency good from the perspective of our calculations, high frequency is also good in terms of stabilizing the states that you get. Okay, so in a way that also gives us more motivation to understand what exactly is happening at high frequencies. Okay. So this the Floquet heating is, if everything goes according to plan, Floquet heating is lecture 4 and pre-thermalization is the final. Okay, final day. So both of these will be covered on Thursday. Okay. Yes. So heating is captured by, so all standard diagnostics that you have probably heard in Krishnendu's set of lectures, right? All of these we use. The only difference is that in the standard version of ETH, because your energy is conserved, you cover the energy shell that corresponds to that initial energy you started off with. So it's microcanonical in that sense, right? Here, because you are driving, you go to an infinite temperature state, so you essentially cover everything. So you just end up at this effective temperature which is infinite. Okay, so that's what we will sort of cover. I will also tell you some. If time permits, we'll tell you some bright stories of how one can evade this fate, possibly. But we'll see how I do on time. Okay. So now what I'm going to do is I'm going to construct for you the effective Floquet Hamiltonian using high frequency expansion. So this part is going to be a little more algebra heavy. So please, ask questions if you are not following up any particular step. Okay. So let me start off by first telling you that there are 3 classes of drives that we will primarily be interested in. So the first corresponds to what is called a kicked system, where UF is given by some U2 times U1. Okay. So what this is, why is this a kicked system? Because you are suddenly kicking the system at a certain time. So the kick corresponds to a certain unitary, and this corresponds to the rest. Okay. Then we have a generalization of these kind of kick drives, which is called step or square drives. Which is something of this form: Ht equals H0 plus A sine omega t H1. So here the evolution gets divided into 2 parts. The UF is e to the power minus I H0 minus H1 t by 2 e to the power minus I H0 plus H1 t by 2. Okay. To contrast, this would have been e to the power minus I H0 e to the power minus I H1 t. So this is a structure which is very similar to this. Okay. So we will use some of these notions to construct a high frequency expansion here. And finally, we will take the case of general sort of sinusoidal drives, which is a continuous drive. Oh, sorry. So the final thing is a continuous drive of Ht equals H0 plus A cosine omega t H1. So to do this, we will use this expansion which is called the Baker-Campbell-Hausdorff. This is a generalization of, this will also be essentially BCH. For this, we will use a generalization of BCH, which is called the Magnus expansion. Sorry, sine of sine function. So it's plus at between 0 to, so in one half it is plus and the other half it's minus. Okay. Generalization of BCH, which is the Magnus expansion.
In that kick system, there's supposed to be a t after e to the I at 0, right?
No, not really. I'll tell you why. The normal kicked Hamiltonian is h equals h1 plus h naught delta t minus nt. So that's why. Okay. So with this, let us start. So, sorry. Okay. So the first thing is BCH for a kicked system. Okay. So the idea of a kicked system is you have some structure like this. I've just written it as some e to the power minus ijh naught e to the power minus ih1 hh1. Okay. If any of these is much larger than the other, then there is a way of getting an expansion. When j is much greater than h, okay, then this hf, which is I log e to the power minus ij h naught e to the power minus I h1. This we can expand, and maybe you have seen this expansion before. The first thing is the average, just the sum. Then the next thing includes a commutator. The one after that includes two commutators, and so on. Okay. So this, what I am doing is that I'm just building this up for any general thing. If you put your t to a different value, okay, it will just rescale one of these. Okay. The goal here is that if I'm interested in high frequency, right, then one of these would be much larger than the other. So we can then do an expansion in one of these. That's the only thing. Yeah. Yes, please.
In this particular case, we did not need to go to a rotating.
No. In fact, what I'm going to do right now is I'm going to just show you what we can do if I can treat one of these perturbatively. Okay. Sometimes what will happen is, and this is what I would probably end with, that I will do this example of the Kapitsa pendulum, where you drive with a high amplitude and a high frequency, and the amplitude scales with the frequency. In that case, you have to go to a rotating frame to be able to use some of these. Okay. So, but this is if everything is well behaved, then we can use any of this. If things are not well behaved, we go to a suitable frame and then use these formula.
Just one query.
Yes.
H is very negative, what will this happen?
Oh, so it's not a problem at all. The way that I am setting this up, I'm just going to write down so what I'm doing here is I'm doing an expansion which I would retain things which are first order in H. Okay. There is an equivalent thing you can do where you can retain things which are first order in J. Okay. So yeah, so that is not going to be a problem. Yeah. As of now, as I have done this, this is how the general expansion looks. Okay. Now you can actually, if you want to retain things which are only first order in H, there is a neat resummation that is known that one can use, and that resummation is the following.
Every higher order commutator, you will get, so let's say first order means, from every higher commutator you will get.
Exactly. Every higher order commutator will have terms which are first order in H. So what I need to do is, see, if naively stopping this is not great because I am ignoring terms, right? So what I am going to do is, I'm going to write down an expression for what happens when you resum these, and I'm also going to give you a reference to a paper where the method to resum it to higher orders has been presented. Now that paper's, the algebra in that paper is, I think, 2 classes worth of work. So which is why I'm just going to give the reference and move ahead. Okay.
What are those terms changed by two in the last commutator?
Oh, H1 comma H0.
So this resum can be given for any H0 or H1 or for
No, it can be the resummation up to, as long as you have one parameter which is much less in value than the other, right? Then you can do this resummation. There is no problem. So the first order resummation you can always do. The second order resummation actually does include, or higher order resummations do not converge at certain points. There is some replica trick of doing it, and they do not converge at certain points and so on. So that's why I'm not going to go into but the first order resummation is very nice. You can get an exact form. So you can write it in this sort of neat form, which is written in terms of what are called the Lie derivatives, okay, which are these commutators. Okay. So, and for higher orders, for this and the higher orders, I'll just leave you with this reference because I want to get to the other ways of summing up things. Is in this paper by Thomas Sayan and Anatoly Polkovnikov and others. Okay. So this is what you get with a kicked system. In principle, summable, in practice needs work. Okay. But we know how to do this. B, one good thing about this is that this generalizes to classical kicked systems as well. If you take this and you literally replace all the commutators, 1 by I commutators with Poisson brackets, you can get an effective Hamiltonian that describes the evolution of classical kicked systems. Okay, so this is generalizable to classical systems. And this is the reference. Okay. So now let me get on to I think what are the sort of more interesting parts which we can actually derive somewhat more of. Okay, so that is the case of these step drives. Okay. Yeah, that's the whole point. Yeah.
Then I said that if I take this lead derivative, the Poisson bracket, then I will get some classical effective Hamiltonian.
You do. So you can get a classical effective Hamiltonian, okay, and that classical effective Hamiltonian can describe the dynamics of a classical driven particle. So in fact, I mean, we once did this calculation for something. That's how I first found out about this paper, where essentially we were trying to help in designing this accelerator, which is essentially the dynamics is actually described by classical driving fields. And then we wanted to get an effective Hamiltonian to find what is the stable region of this accelerator. Okay, so this substitution actually works out, and it will give you, to first order. For certain simple cases, what happens is, even though this is a general expression, you can actually do this resummation. For complicated many-body system, this summation holds, but it's difficult to do it. But for classical particle moving in a ring with some magnetic field being pulsed on at various times, you can actually do this resummation. And then when you have done this resummation, you can match it with what you get classically, right? And it works out wonderfully well. So the in principle generalization holds for any classical many-body system also, but then the complexity remains that this doing the lead derivative is hard work generally. Okay, so that's what.
So another question is that at higher orders, when I'm getting the leading order term, leading order term in linear in age, then the results are getting more and more long range. So each is
Yes.
And also if you take this J to be the order of A,
Yes.
it's no longer sparse.
Yes.
And so in classical sense, that will mimic the long range system.
Yes, it's actually, so it's not just long range, it's actually multi-body. Okay, so one of the things, and this I will try to again come back on our last talk, there is not a lot of difference between classical and quantum periodically driven systems. A lot of these mechanisms that I am telling you, all of these port over, and so many of the phenomenology in quantum many-body systems also go over into appropriate classical many-body systems. Okay, but there are certain things. There is one thing that you can't get classically, which is these quantum interferences. So what you can do is you can, by driving properly, you can design quantum interferences that do not have classical analogs. Okay, so there are certain things which are specific to quantum, but much of the phenomenology can actually port over into classical. Okay.
So this expansion for HF, there's this complicated thing.
Yes.
Like, is this just a formula, or there are some, like, something you can say about HF?
So this is just the two things. One is that even though this is the formula, this resummation has been done. So if you have an algebra where at a certain order these commutators finally vanishes and goes to 0, then you can actually resum this. And also the other place where you can do this is if you have single particle driven systems. So there it's also possible to get this resummed. Okay. For many body driven systems, typically you won't get something very nice out of it, but you can still do something with it, because at least there's you at least know a closed form, right? So this is the kit. So now let's get to the step. Okay, and in this, the step is where we are going to sort of first introduce this high frequency thing better. So is the step drive. And in the step drive, I'm going to take a very simple form. I will say that during the first half of my drive, I'm evolving with some Hamiltonian H naught, and in the second part, I'm evolving with some Hamiltonian H1. Okay. Now, both of these have T that is coming. So now you can see that you can do a high frequency expansion because both of these carry T's. So you can, all the orders of the commutators will be something which is some order in T. Okay. So let me write down the commutator thing for you. So this HF, which I'm again going to use the Baker-Campbell-Hausdorff, the step one that I had given had H0 plus H1 and a H0 minus H1. I have just redefined the H0 plus H1 as some new H1. And yeah, so it's not different. It's still the same. I am just using this because it makes my writing simpler. Yeah, life simpler, yes.
How is it different to the earlier one?
Yes. You see, now in this one, every order of the expansion comes with T to the power alpha, right? So now you can see that this will build into an inverse frequency expansion because these are the inverse of the frequency, right? So this is, so there if you see the original kicked thing, if you have a kick, you have one of the terms comes with a T, the other does not. So a kicked model is typically of this form. H is some H naught plus A sum over N delta T minus NT. So this term comes with T, this one does not. Okay. So then the expansion will always be by collecting one of these terms, right? Because both of them don't carry T. On the other hand, here every commutation term comes with T, T squared, T cubed and so on. So now this is easier because I can stop at a certain order of commutation and say that, oh, I have done it to this order in T, right? So that way this expansion is more tractable than you don't have to do that Lie derivative. Okay. There are two reasons why I sort of did this. One was also for completeness because kicked systems do appear a lot, but also to drive home the point that doing these kind of expansions for kicked systems can be very tricky and difficult. But once I have a system which is step driven, then life becomes simpler. Okay.
Here also, if you reach this HF to be a fundamental expansion in terms of amplitude, then
Huh.
you need to resum again.
Yes. If you want to do it as in terms of amplitude, we'll resum again. But what I'm doing now is considering that situation where H0 and H1 are non-commuting, but are roughly of the same energy scales, and both of them come now with this T. Okay. So then, because both of them come with T, we are saying that T now controls the order of the expansion.
It's very small parameters, high frequency.
Yeah, has high frequency, precisely. Yes.
Relatively nice question. So, kick and step. If we look at the step UF and
Yes.
we define, let's say, some t, and so in the first exponential we can write t minus x. What I'm trying to say is that kick is kind of a limit of the step function, where
Kick,
if we take one of the t over 2 as to 0 and the other one which naturally will become t.
but you cannot really, if you took it to 0, no,
Yeah.
this will vanish. So, yeah. So that's why kick. So two things. One is that so that's why kicks require a little more care, but kick systems appear naturally in many contexts because you can always sort of put in these magnetic field drives which appear in the form of kicks. We won't get into this too much, but one of the first sort of important examples of a driven system was something called a kick top, which was used to first study quantum chaos. So that also has a kick. So kick systems do appear at a lot of places, but dealing with pure kicked systems is a little difficult because you can't really do an inverse frequency expansion. So all that you can hope for is one of the amplitudes is less than the other. But once you get into this step drive business, now you can do this inverse frequency expansion because you can cut off the Magnus expansion cut off this commutator expansion at a certain point, right? So this is also, although this is BCH, this also goes by the name of Loche Magnus. So these are just the terms up to third order. The first one is the average. The second one includes commutators. Third one includes commutators of commutators and so on. Right? So this gives us this structure of something called the Loche Magnus expansion. Sorry, 1/12. This term here. Yeah. This comes from BCH. No? The BCH expansion has this 1/12. So up to this order, you can actually do it by writing. If you write it down and collect terms, it's a pain, but it's possible to do it. It gets progressively worse after this. This n?
Omega to the power.
Oh, this is, yes. Sorry, you're right. This is 1 by omega to the power n. Okay. So this is the spirit of the general Loche Magnus, that we want to do a time evolution or we want to look at a driven system and we want to expand it in a power series that scales with n. Okay. Now, okay, let me briefly tell you then that how the general case works. Okay. Oops. So now let's say that I have a generic time dependent or generic periodically driven Hamiltonian. what do I do? How do I do this? Okay. So what I need to do is the following. I need to write down the general Fouquet time evolution operator as a time ordered exponential, right? And then what I want to do is I want to write it as e to the power minus I t h r. Sorry. So I have on the left hand side I have this, on the right hand side I have this. So the left hand side we know what to do with this. We want to write down a Dyson series. Okay. So, and what we'll do with the right hand side is we will write it as an inverse Fourier expansion, inverse frequency expansion. Okay. So let me let me do this. Let me at least try to tell you how this will work. Okay. Going forward, one of the things for the rest of this is I'm going to notationally use h tj. I'm going to substitute as h of j. Okay. What I'm going to do is I'm going to tell you how we get the time averaged Hamiltonian, which is perhaps easier to get, but also the sort of first order correction which has one commutator. Okay. The second order, if you want, you can sit down and do it. Okay. It's not that difficult, but it's a little tedious. Okay. So then let us start off by first expanding the LHS. So this is my, let me call this my LHS. This is my RHS. So my LHS is identity minus I 0 to t dt1 h1 minus 0 to t dt1 0 to t1 dt2 h1 h2. Okay, plus dots. So this is the time ordered exponential. This you remember, right? This is how it works. Good. Now let's move ahead with this. Let me sort of wipe off some part of the board. So what I have done is I have just taken this notation of htj equals hj. Okay. When I was first deriving this, I got so confused with all my notation flying everywhere. This I found to be a notation that at least I could follow. So hopefully you can also follow. Yeah. Okay. So this, you can see this is going to be of order t. Okay. This next one is going to be of order t square and so on. Okay. So what I have to do then is, if I look at the right hand side expansion, that has identity minus it hf0 plus hf1 plus dots plus IT square by 2 HF0 plus HF1 plus dots, right? So my inverse frequency expansion tells me that HF0 is of order t to the power 0. So if I am only interested in connecting to the order t term, then I only need this term. So HF, if you remember, what we have done is the total HF I have expanded as a sum over n equals 0 to infinity HFn, where HFn is proportional to t to the power n. Okay? So if I try to use a little bit of colored chalk, no, so it will have one commutator, but it's a little complicated. So all that we're doing is, see, I have expanded this out here. I'm trying to match the left hand side and the right hand side. Yeah, so just now, so as you will see that commutators will come in. So eventually, see, this is a generic time dependence. So if I specialize this generic time dependence to the case of the step drive, I should get back the commutator. So you will see how the commutators come out. No, this is how I have expanded my HF. So I can always do an expansion in the high frequency regime. I am doing an expansion, so high frequency means low t, right? I am doing an expansion in orders of t, and I am just reading off what they are going to be. Okay. Then in the next one, which will be order t square, these two would contribute, because HF1 is proportional to t, and t multiplied by t will give me t square. Similarly, HF0 was proportional to t to the power 0, so this will also contribute.
In that I t squared term,
yeah,
are those HF like squared something?
Yes. So basically this will be, yeah, I'm sorry, you're right. Yeah. So these are the terms that we have to account for. Okay. So let us first then see what is the first order term, and then we will do the second order term, which will take a little bit more work. Okay. Okay. So the first order term is actually in some sense easy, because see, this is the only term that contributes to first order, right? And this is the only term that contributes to first order, right? So the first order term is just this. Good? Okay. So now comes the tricky part. Now what I have to do is collect these terms, substitute the value of the first order here, and then obtain what's my final result. Okay? Okay. So at this point, I have a question for you. You decide what you wish to go with. One option is I just give you the second order result, because it's just algebra. I can work out the algebra, but it's just algebra. Okay. and I give you an example after that, or I can work out the algebra. So what would you prefer? Example? Yeah, very good. I would have preferred an example myself. Okay, so let me just tell you what the second order looks like, and then we'll do the example.
That is the HF1.
This is the HF0 actually. Yeah. I will just write down what the other term is so that you know that this does include commutators. So this is the, if you do this algebra, you will ultimately end up here. Okay. If you do it to the third order, it's not very difficult, but it's just you have to collect terms. Okay. So what I suggest is you try to do this, and if you get stuck, we can return to the algebra. Okay. Good. So let me now do an example to take a break from all of this. And the example that I'm going to do is actually a very nice example, I quite like it. It's the example of something called the quantum Kapitsa oscillator. So you remember the Kapitsa pendulum? What would classical mechanics is the standard problem that my pendulum, there are two fixed points, one of them is stable, so you get small oscillations, the other is unstable, but by driving it really fast, you can stabilize the oscillations around the top, right? So we will do a quantum version of it, and we will figure out under what conditions do you get a stable oscillations. Okay. So here is my Hamiltonian. So there is a kinetic term. I have set things like mass, etc. to 1. So p theta square by 2 minus omega naught square. This is the potential term plus a omega sine omega 2 cos theta. And inverted stable inverted equilibrium for E much greater than omega naught. And then the question is that when would you get a stable inverted equilibrium? When would you get an equilibrium that is stable around theta equals pi? This one? Yeah, it's just this, I am doing this this wherever my theta is, right? So what I'm doing is just I'm driving it with essentially ml square, so cosine square theta, right? So or ml square cos theta. So that's so if you want to do it with positive also, I mean you can do it. It's not a problem. But yeah, at least I seem to have a negative here. Okay. So so if one of the things that I cannot do with this Hamiltonian is I cannot take a naive expansion. I cannot take a naive Magnus expansion to get the effective Hamiltonian. Okay, and that's because of this term also scaling with omega, which means that if I treat this as H kinetic and if I treat this as H potential, And if I were to take this kind of Magnus expansion terms, then I would have terms which is 1 by omega h kinetic plus h potential sorry this is the so I would have commutations with this term that scale with omega. So the whole point of doing inverse frequency expansions were I could do this expansion with in powers of omega. Here you would have these commutators where the omegas cancel out because the term inside also scales with omega, right? So you cannot do a naive averaging here, right? You have to be careful. Now you have to go into the rotating frame. Yeah, so whatever we had done previously, so I think the fact that why did we do so much of hoo-ha about the rotating frame, right, is purely because of this, because if I were to really do this in the lab frame, I would have to find a way to resum an infinite number of terms corresponding to all these omegas cancelling out. Once I do a correct rotating frame transformation, I will be able to use the standard Magnus expansion. Okay, so the Magnus expansion in the rotating frame is actually an infinite resummation of terms in the lab frame. Okay. Is this point clear? Okay. Yes, yes. I mean, I would have expected it not to be clear after 1 hour 22 minutes. Okay. The point is the following. You see, if I look at the commutations of this Hamiltonian, so this was the part which is time independent. This is the part which is time dependent, right? When I do this kind of, when I try to obtain this Magnus expansion, right, all of this works only because we can do an expansion which is overall, it's an expansion which is in the inverse of the frequency, right? What is happening here is that this drive term scales with omega, which means that at every order I have terms that get cancelled out. So for instance, if I go to the next order, I will have terms in which there will be 2 h drives and 1 h kinetic plus h potential. Both of them would come with omega square. It would cancel out with 1 by omega square. Same for omega cube. Same for any omega n to the power n, right? So if I have to do a proper inverse frequency expansion, I would have to collect all terms, right, corresponding to one order in omega. I have to resum them, right? So this is an infinite resummation, and this is where my life becomes very difficult in the lab frame. Now, if we are able to do this rotating frame technique that we had been doing for so long earlier, what I will show you is that there is a nice rotating frame sort of transformation you can do. What that will do is it will get rid of this and put this in here, right? And then you will find that you will be able to do the standard Magnus expansion in the rotated frame. Okay, and and that is why, in some sense, all of this doing this transformations into the rotating frame, that becomes important. Okay. Okay, so let me.
So the term that will come to the p theta, that would be proportional to omega.
No, so now what we will do is that, so I'll just show you what we'll do. I'm going to add this something that will make my I p dagger p dot t p dagger will cancel this off, and then we have to look at the effect of that on this. Okay, the effect on this is non-trivial, but it's something that we can account for. So I'll just show you how that works out. So the p of t that I want is exponential I a sine omega t cos theta. Okay. You can see why this is going to work out, because this will give me a omega cosine omega t downstairs, right? A omega t cosine omega t cos theta. So the rotating frame Hamiltonian becomes p dagger p theta square by 2 p minus omega 0 square by 2 cos theta. This only depends on theta, so this will commute with the second term. So all that you need to do is to find out this p dagger p theta square p, which is essentially half of p dagger p theta p p dagger p theta p. Right? And what this will do when you act with this p is it will shift it, right? So it's the same way in which e to the power I pa x e to the power I pa shifts x, right? So what this will give you, this particular term will give you, is p minus a sine omega t sine theta. And the result of that's p theta, yes, that's p theta, yes. So the result of doing all of this is a Hamiltonian which looks like this: half of p theta minus a sine omega t sine theta whole square minus omega 0 square cos theta, right? Nothing here scales with omega. I can take the average Hamiltonian, I can take the effective Hamiltonian, right? So let me just tell you what the effective Hamiltonian is, because really I have been rambling on for too long, so I should stop. But to first order, the effective Hamiltonian that you get if you do this is p theta square by 2 plus a square by 4 sine square theta minus omega 0 square cos theta. Okay. So this now is a particle which is now in this effective potential V theta. All that you need then is that if this effective potential should be something which is stable. So of course the first thing is you need to find wherever V theta has extremas. So if you do V prime theta, right, so then this has extremas both at 0 and pi. And if you do del 2 del theta 2 of V theta, V effective theta, let's call this, this is equal to omega 0 square cos theta plus a square by 2 cos 2 theta. If you want it to be stable at theta equals pi, then this over here, this must be greater than 0, and a condition that you would get for stability from this is minus omega 0 square plus a by 2 is greater than 0, which implies that you have to drive it with a critical amplitude which is greater than square root of 2 omega naught. Okay. So, the Magnus expansion is often very useful. It is pretty much the only thing we can do. If you can do a naive Magnus expansion where none of the Hamiltonian, none of the terms grows with the frequency, then you just use the standard Magnus expansion formula to look at what are the effects beyond the average Hamiltonian. If it grows with the frequency, then find a nice rotating frame where you can do this infinite resummation of terms and get the Magnus expansion in the rotating frame. So, yeah, so that's it for today. Tomorrow we will sort of get into something called the Sambe space formalism, and we will look at we'll start to look at something called the Floquet Fermi golden rule. But yeah, thank you for listening. If you have any questions. The last line is, see, I want to look at when is this stable, right? One is this is an extremum, but when is this stable? So to find its stability, what I do is I obtain this thing. I look at this delta 2 del theta to v effective theta, which is this. I demand that this must be greater than 0. This whole thing must be greater than 0 at theta equals pi. Only then will it be stable at its inverted point. So when I demand this, what I get is A must be greater than 2 omega naught square in order to, so actually this is A. So A must be greater than AC, and AC is square root of 2 omega naught. So when this happens, I stabilize the pendulum at theta equals pi.
How does this result compare with the classical result? There must be some h bar, because you have set h bar to 1, so somewhere it is hidden.
Yes. So I think, so I don't recall, so it is something very similar, modulo exactly this h bar, but I don't exactly remember. But I mean, essential, yeah, I think for one thing that as I was mentioning, that most of these classical and quantum results are the same in Floquet. So I don't exactly remember this, but I suspect it will be something very, very similar to this.
If it would be the classical case, then what would be different here where it is?
So what we have done here is that we have made these transformations, right, with this p dagger and p and so on. There you have to do these canonical transformations if you want to do this transformation into the rotating frame. Okay, but once you have done the, I mean, all of these are equivalent. I mean, there is a canonical transformation. This I p dot p becomes the Coriolis force and so on. So you can do all of that. So those are the parts that are different. Other than that, this average Hamiltonian, once you have done it, it would be the same. So this is a good point. I don't remember it, but I think I'll look it up. I suspect it will be very similar.
Yeah, because there also one comes up with an effective potential.
That's right.
To deal with the Liouville equation.
That's right.
Expand the Liouville operator.
That's right. Yeah. I mean, much of it is just, it's not maybe surprising, but I'm still sometimes just, I find this very interesting that much of these do not require quantum mechanics at all. There are only fine-tuned places where quantum mechanics actually shows up. Much of the physics is actually classical.
Any other question? Then let us thank the speaker.